Now that we have embodied row operations with elementary matrices, we can actually revisit some topics where we used row operations in kind of a mystical ad hoc way. And maybe the most important example of this is when we calculated the inverse of a matrix. So remember, when we did that, what we did was we took a matrix, the matrix we wanted to find the inverse for, we augmented with an identity matrix, we did row reduction, and on the left-hand side, right, assuming that we were able to find an inverse, then A reduced to an identity matrix, and then magically the inverse matrix appeared on the right-hand side here for some reason. Well, let's explain why that really works. So one way to think of finding an inverse matrix is what we're really doing is solving this equation here. A times some matrix X is the identity matrix. If we can find such a matrix X, then that matrix X will be the inverse of A. So, right, just keep in your mind as we do this that X is really the inverse of A. Or hopefully, if we can find it, it is. Okay, well, now that we have elementary matrices to do row operations, we can take this equation and start doing our row operations, right? There's some sequence of row operations that this row reduction used, and each one of those row operations has an elementary matrix associated with it. So let's suppose that the first row operation is associated to some elementary matrix E1, and then the next row operation, as you do this row reduction, is embodied by the elementary matrix E2, and so on. And let's say it goes up to E sub k. So k is just the number of row operations that you had to do to reduce A to the identity. So in this equation, what we can do is multiply on the left-hand side of both sides of this equation with our first elementary matrix. Right? That really is the matrix form of doing the row operation, is multiplying on the left by your elementary matrix. So on the left-hand side of the equation, that gives us E sub 1 times A times X equals E sub 1 times the identity, but E sub 1 times the identity is just E sub 1. Okay. And now we can multiply on the left by E sub 2, right? And I do that, let me write that in a new line actually. So now multiply on both sides of this equation, multiply on the left by E sub 2. So that gives us E sub 2 times E sub 1 times A times X equals E sub 2 times E sub 1. Okay. And then, right, do your next row operation. Just keep doing row operations until you get to the very last one. So eventually we get down to E sub k times E sub k minus 1, and so on, all the way down to times E sub 2 times E sub 1 times A times X equals, and then on the right-hand side is just all of our E's again. So E sub k times E sub k minus 1, all the way down to E sub 2 times E sub 1. Okay, now remember, multiplying on the left by these elementary matrices has the effect of doing those row operations to the matrix A. So this collection, this big matrix product right here, this is the matrix A, but with all of these row operations done to it. But we're assuming that we can reduce A to the identity matrix. So if you start with A and do all these row operations, you just get the identity. So times X equals E sub k down, product down to E sub 1. And the identity matrix times X is just X. Okay, so we found a solution to this this equation. So whatever this X is, right, we can genuinely call this the inverse because it's a solution to this equation. But notice it also gives us a formula for what the inverse is. The inverse matrix is given by just the product of all of these elementary matrices, right? In fact, you could even stick the identity matrix on the right-hand side. So what this says is that the inverse matrix, the inverse of A, is just the identity matrix, but with all of these row operations done to it. And that's what we see over here. The inverse, the reason that this A inverse shows up right here is because we started with the identity matrix and we did the exact same row operations to the identity matrix that we did to A to reduce A to the identity. So this really explains why our calculation trick, or this is a more matrix-oriented version of why our trick for calculating an inverse matrix actually works.